When the stars play peekaboo, I'll serenade my Lou. When Dixie stars are playing peekaboo, I wander down for to see my Lindy Lou. Oh, Miss, I'll start hooting. Bullfrogs commence to tooting.
Okay, in the last little bit here, we need to talk about the sun. We're going to talk about stars, galaxies, some stuff that is in the end here. You see that chapter 45 talks about the sun. There's some good information in there. This is kind of a funny old picture, but you know from the Greek myths, of course, that the ancients imagined a being that had this radiant crown, and he would ride his chariot through the stars or through the sky, and thereby bring light to the earth. We know a little bit more than that today. Here is a picture that strips away the layers of the sun so that you can see what's down inside. Of course, we have the surface of the sun out here on the outside. The surface is called the chromosphere, and once you peel that away, then you see that there are other sections in there. There's a convective zone right here. That's a little bit like the mantle of the earth, right? You've got the crust out here, and then down inside you've got the convective zone. It's not anything like the mantle of the earth, in that the mantle of the earth is rock, and this is hydrogen gas, but it's that next layer in. The radiative zone is inside that, and then down in the center you've got the core. So again, it's 4 layers. You got core. Outside of that, you got the radiative zone, followed by the convective zone, and the surface here is referred to as the chromosphere. There is a photosphere here as well, which is kind of the outside of the convective zone. There are little spots that you can see, little sunspots. Those are interesting, and I've got some other pictures of that for you somewhere coming up next. But here in the core is kind of where everything's happening. The tremendous heat and pressure there push hydrogen gas together, and through a long process it becomes helium. You can think about 2 hydrogen atoms being mashed together. There'd be 1 proton, 1 electron in each hydrogen atom. That would give you 2 protons and 2 electrons, which is helium. It's not quite that simple, because the first or the second proton really becomes a neutron, and then you got to get another one and stuff. You can look that up if you're interested. But hydrogen is becoming helium. When you do that, tremendous energy is released. We can do that here on Earth. We can do it one of 2 ways. One, we can build a hydrogen bomb, an atomic bomb that uses hydrogen and fuses it together into helium. The other way, we can build reactors that do fusion reactors. They're very expensive to run, and at the moment we have to spend more money to make that happen than the energy that we get out of it. So we don't have fusion reactors here on Earth except in research labs stuff. If we could find a cheap way to do it, though, that would be much nicer than the fission reactors that we currently have up here at the Catawba plant and different places. They take heavy elements like uranium or plutonium and break that down. You get tremendous energy out of that too. The nice thing about fusion is that you don't have all the radioactive waste laying around for 20,000 years or something. So fusion, if we could get it to work, would be a beautiful thing. Y'all get to work on that now that you're scientists, and we'll see if we can't make a better world here. Again, remember the diameter of the Earth was something like 155th of the diameter of the Sun. So you know that there's this is a big ball here. It's millions of degrees in the core here. The surface of the Sun something like 10,000 degrees Fahrenheit. So much cooler, but it's still way too hot to even contemplate. It's got these prominences, these flares that jump up off the surface. Just tremendous amounts of energy being released here in the core. It radiates out through the radiative zone and then the convective zone here, you get convection going on. That energy heating the surface, it swirls it and it releases it from there. All that energy sweeps out through space, coronal streamers and the like. So that energy comes to us, it warms our planet, it lights it up. We have day, we have energy. Here is the information about the sunspots that I mentioned. Here you can see some of those little spots, and that's all we're talking about. These are little dark spots on the surface of the sun. People have been watching these for a very long time. Here's some data back to the mid-1800s, although there is data farther back than that. The interesting thing is that when you graph these sunspots, they make a pattern. And I think you can already see the pattern here as well as here. There's an 11-year cycle on these sunspots. And what happens is they start off north and south of the equator here, about 30 degrees south, 30 degrees north. So that would be in a region here and here. And then over the 11 years, they will work their way to the center, like you see right here. So these dark spots will move into toward the center, and then they kind of disappear and pop back up out at 30 degrees again. And so there's that 11-year cycle of these things. You can see them working their way toward the equator of the sun there. All right. If you graph them, how many there are, or rather the percent of the visible hemisphere of the area, these are pretty small dots, right, on the whole surface of the sun. So maybe we're talking, 0.1% or something that's covered there of the sun. Here you can see that there's virtually no sunspots. They build up to 0.1%, 20%, maybe even as much as 0.5%, and then back down. But again, there's an 11-year cycle, up, down, up, down. So that's pretty interesting. That 11-year cycle affects some stuff on Earth, radio transmission and weather and drought cycles and all sorts of things. So that's an interesting thing and a neat pattern that we can kind of play with. The stars are like the sun, right? Our sun is a star. It's a big ball of hydrogen being fused into helium, and all the other stars are like that too. There are some differences, and we'll talk about those, but our sun is a star. Here, I got some terms to begin with. The brightness of stars. There's about 3 ways here that we can measure the brightness of stars. Luminosity is the actual amount of light that's put out by the star. The apparent magnitude is how bright it appears to be here from Earth. Of course, that if you take a flashlight and you turn it on, put it right up to your eye, that's going to look pretty bright. Okay? If it's all the way across the room or across a field, it's not nearly as bright. So you know that not only how much light the flashlight puts out, but also how close it is to you makes a big difference. And so that's the idea with the apparent magnitude. How bright does the star appear to be from Earth? This one, though, luminosity, says how bright is it in reality. A compromise is this absolute magnitude. If we could line all the stars up at the same distance away and see which ones of them are brighter or dimmer, then that would be measuring the absolute magnitude of these things. The distance that we pick is called 10 parsecs, which is about 33 light years, and you see it in kilometers there. But if we could line up all those stars at the same distance, at the distance that it would take the light 33 years to get to us, then we could measure this absolute magnitude. I've got here a chart that's called the Hertzsprung-Russell diagram. This is an important chart, and what you see is that there is a line that kind of runs here through the center of this thing diagonally, and about 90% of the stars lie somewhere on that line. That's called the main sequence of stars. And here you see a dot for the sun. It's a nice little yellow dot. It's not real big. It's not real small. You look down here at the bottom, they're graphing temperature, right? It's about in the middle there. Not too hot. The hot stars are over on this end. Not too cold. The cold stars go to the other way. And so again, it's not too hot, not too cold, not too big, not too dim. It's not too bright, not too dim. It's just right, and that's the way we like it. The exceptions down here are the white dwarfs and the giants and supergiants. So stars kind of live on this line right here. The main difference is how much mass they have, how much gas they have to work with. If they have more gas, then they're going to be bigger, they're going to be brighter, they're going to be hotter. If they have less mass, you slide down the other way, they're going to be dimmer, smaller, cooler stars. All right. When stars reach the end of their lifetime, they swell up into giants or supergiants, depending on how much mass they have. And then eventually that star will explode in what we call a nova or a supernova. And what's left behind is the core of the star, which is a white dwarf, which can cool on off into what we call a brown dwarf. So those dwarf stars are kind of what's left over when a star explodes. These guys are getting ready to die. These guys are in the middle of their life, doing just fine. All right. Here's a little chart that shows kind of what happens, the whole course of a star's life, or the cycle of it, if you will. A nebula is a cloud of gas, and so there's gas in the universe. If you know, of course, that this gas, mostly hydrogen, has mass, so gravity works on it, and the gas molecules pull together, and they begin to bunch up. They form what we call a protostar. It's not a star yet, it's just a big ball of gas. It's swirling around because as gravity pulls it kind of swirls it in almost like a bathtub drain, you know. And it is going to collect there. The core of that thing starts to glow hotter and hotter. When you have enough mass, when this thing is collected into a ball, boom, you get a nice star. The thing kicks off into fusion, and it lives the main sequence. So this is kind of the main sequence part of the Hertzsprung-Russell diagram we saw before. At the end of its life, it's going to swell into a red giant. If it's not terribly massive, it will swell into a supergiant. If it is a massive star, the red giant will explode like you see here, leaving behind the core, which can go white dwarf, cool off into a brown or black dwarf. This gas right here, though, that is cast off, forms another nebula. If it's a big star, you got a supergiant, blows up with what we call a supernova, and again, that core is left behind. Gas is thrown out into the universe. That gas comes, makes a nebula. All right. And the nebula collects gas together, makes a star, makes a nebula, makes a star. It's just a cycle, goes round and round. A couple oddities here. The core of the supernova could be a pulsar. A pulsar is a star that kind of rotates and it emits radio waves at a regular frequency. It's almost like the sweep of a lighthouse going beep, beep, beep. And when we first found these things, we got kind of excited about them because it looked like an intelligent signal. And some people said, wait a minute, that's just a star rotating. Right here, if it has enough mass, if the core of this thing has enough mass, it becomes a black hole. And those are pretty interesting creatures too. The black hole, everything gets sucked into a black hole that gets within a certain radius, the Schwarzkopf radius. And even light is sucked in to this thing. It's got enough mass to just eat everything up. All right. There is almost certainly a black hole at the center of our galaxy. There's probably a black hole at the center of all galaxies. And as galaxies crash into each other, then those black holes combine and make an even bigger galaxy. And so everything's changing up in space, just like here. In chapter 47, we're talking about the universe. Here again, old-timey picture. You know that the Greeks had names for all the constellations. We still use those names, but to them, these were stories. They were myths. They were actual characters that played heroic or less than heroic roles in these stories. And so when you look up and you talk about the constellation Andromeda or Perseus or Orion, those all have tales associated with them. And if you want to grab a mythology book and study up on that, that's some neat stuff, some neat stories, and you can see how it relates to their view of the sky. But today we know that we live in a galaxy. The solar system, remember, was a star and everything that went around that star. So we've got our sun, the 8, 9, 10, 15 planets that are going around, depending on what you count. They have moons, there's comets, there's meteorites, all that stuff we talked about on the last video. You take a couple 100 billion of those stars with their attendant planets and comets and meteorites and everything. A couple 100 billion of those things form what we call a galaxy. So billions of stars here. They're all swirling in a similar pattern to the way the planets go around the sun. It's a very flat disk, like the solar system is a flat disk. And our particular galaxy is referred to as the Milky Way galaxy. If you've ever been way out in the country and you look up in the night sky and you see kind of a hazy band running through the sky, those are the arms of the Milky Way galaxy. We are in that flat disk looking out through billions of stars. It's about 100,000 light years from one end of the Milky Way galaxy to the other. If you wanted to cross it, and if you could go at the speed of light, it would take you 100,000 years. We're something like 30,000 years from the center of this thing. So we're out in the frontier. We're in the sticks, and that's okay. It gets pretty crazy in the center. Again, you got the black holes. You got stars much more tightly packed. You can see that here, and so we like it on the outskirts. It takes about 200 million years to go all the way around for this whole pinwheel to spin around. Is 200 million years. So the Milky Way galaxy is a neat place. It's home. There's, depends on who you ask and the most recent count, but something like 200 to 400 billion stars in the Milky Way galaxy. We're finding planets around some of these other stars. We're up around 500 planets that we found on other stars that are in the galaxy. We can't see well enough to see out of the Milky Way galaxy. You can see here that there's a little dot of light that could well be outside of our galaxy, but it could be another galaxy, right? There's billions of these galaxies floating around. We didn't even know that until the 20s. We thought they were just individual stars or that they were clouds of gas nebulas or something. And Edwin Hubble came through, and he had enough resolution in his telescope to identify some shapes and say, no, that's another galaxy out there. Just exploded the number of stars and the size and our understanding of the universe. There are islands of stars called galaxies, and lots of those. This is what you might see if you went way out in the country on a cold winter night and you looked up in the sky. You might see a hazy band, kind of like you see here. It's millions of stars, and you're looking through the disk of the Milky Way. Here's another picture of the same thing, kind of a 360 view of it, but again, that band that runs through the center there. All right, lots of other galaxies. They tend to have one of three shapes. Some of the shaped galaxies are kind of elliptical. They're just kind of egg-shaped or football-shaped or something. Most of them are spiral-shaped, like you see here. This is usually referred to as a barred spiral, though it's got that bar across the center and then the swirling arms coming off. Ours is probably more like you see here, a spiral galaxy, whereas this has that bar going across it. You also have irregular galaxies where they're just kind of no distinct shape or whatever. Here you see two galaxies that are colliding and that will merge and make one galaxy. So these things change over time. Here's some rough estimates, and again, these numbers change depending on whose count you use and the estimates of the number of stars, the number of galaxies and stuff. But just to kind of throw some numbers out there, something like 400 billion stars in a galaxy. There's something like 80 billion galaxies. You multiply that out, it's like 3 times 10 to the 22nd stars. Okay, and that's a pretty rough number, but I mean, you can imagine just this huge number of stars out there. Let's say half of them have planets, right? And of the stars that do have planets, we've got 8 or 12, depending on how you count. Let's say 10, just to make it easy. You multiply this number by 10, that's a lot of planets. Are we the only planet with life on it? Probably not. But we're the only one that we found. We're the only one close enough to really provide a comfortable life. Everywhere else we got to take air. We got to, battle extreme temperatures, hot, cold, whatever. So, interesting questions. No real answers yet. We talk about the constellations. Here you can see some of the constellations. These are just jumbled in. They're not necessarily in this order. But we talk about the Little Dipper. You can see that here. It's like a little cup, right? Cup with a handle on it, like a ladle or something. There's also the Big Dipper. Obviously, these are not to scale. But again, the stars of the handle, stars of the cup of the Big Dipper. Those are actually asterisms. Little Dipper is in a constellation called the Little Bear, or Ursa Minor, and the Big Dipper is in the Big Bear, Ursa Major, and there are more stars to it, but these are the parts that we can see, and so we kind of draw those lines and say, well, those stars kind of go together, so I'm going to make a picture out of them and learn where they are. Cassiopeia or Cassiope, either way, is another one. Looks like an M or a W in the sky. Leo the lion, you can see the head here and the body and the legs. You got to be a little bit creative to imagine these shapes. Cygnus the swan is a big cross in the northern sky, and people had stories about these things, but they meant things too. And when you saw certain constellations come up in the sky, you knew it was time to plant crops or to harvest crops or to get ready for winter, or to, they knew the sky, and we've lost all that. We just look at a calendar now, or our GPS, and we've lost some of that technology. But pretty neat stuff up in the night sky. Here are some of those constellations. I'd like you to learn a couple constellations here, and the ones that will be easiest, I think, would be the Little Dipper and the Big Dipper. You can see the Little Dipper right here. Right there's the handle and the little cup. So that's a nice one. The star at the end of the handle is the North Star, or the Pole Star. So that one's right there in the center. For us, it would be about 35 degrees up from the horizon if you look north. And what's going to happen is the whole night sky is going to rotate around that star all night long. So stars are going to come up in the east, they move overhead, and set in the west. And so imagine this whole disk spinning all the time. The stars aren't moving, the earth is rotating, right? But that is the axis. That's the nail in the wall, and this disk is spinning around it. Little Dipper's right there, so it's going to make a little circle. Right here's the Big Dipper. You see the handle and the cup there. And so that's the Big Dipper. You can also see the other stars there of Ursa Major. There's the body of the Big Bear, the legs, and the neck coming off that way. But we see these pretty easily. As light pollution gets more and more, as we put up more parking lights and more safety lights and more night lights and stuff, we lose more and more of the night sky. We can't see it anything like we could 50 and 100 years ago. So that's kind of tragic, but nobody looks up there anyway, so maybe it's okay. I don't know. These two stars, on the cup of the Big Dipper, if I draw a line from this one to this one and keep going, see how it comes out at the North Star? So that's a nice way to find north in the night sky. Find the Big Dipper, chase those two stars, and keep going until you get to the North Star right there. We talked about Cassiopeia. There she is. Those four, or those that little M or W right there. Again, it's going to spin all night long. So those are some that would be good to know. Little Dipper, Big Dipper, Cassiopeia. There's the North Star. Lots of other good ones up there. Orion is an excellent one to find in the winter time. In the summertime, he's hiding, but that's good. One more slide here. This one's also about constellations. There are 12 constellations that are thought to be pretty important. We mentioned the term the ecliptic. Said that was the path that the sun appears to follow as the earth rotates. And so if we draw it from above, here's the sun. The earth is moving around like that. And what that means is, for example, here in May, if I look at the sun, draw a line, it's over here in Aries. And if I look in September, then the sun appears to be in Leo, or January it appears to be in Sagittarius. So we kind of ascribe a certain importance to these constellations because the sun moves through them. There are 12 of them here. You recognize them as the stars of the zodiac. And some people believe you can look in the paper and find out some secrets about your life. I don't know that that works all that well. I wouldn't recommend it. For example, I'm born in late April, April 28th, which would be about here. And if you draw the line, then the sun would be in Aries. However, people that are born in late April are supposed to be Taurus. And so you can see that the whole thing's off by one. Remember, the earth has that wobble to it, the precession that takes 26,000 years. So what happens is they set up this system, and over the course of time it's all shifted, and I'm not supposed to be a Taurus anymore. I'm supposed to be an Aries. I don't know what that means, but it's an interesting conundrum, I suppose. All right, that's all I have. The constellations are great. Space is great. Lots of interesting stuff about astronomy, and hope you enjoyed it. Thanks so much.